All right, let's look at notes G. But first, we're going to start with the good corny math joke. Why do plants hate math? Because it gives them square roots. All right, so as I mentioned, we are in Module 3, Notes G, and we are looking especially at function composition. Now, once we talk about function composition, that's going to lead us into something called the difference quotient, and then we're also going to look at function decomposition. Now, when I think of composition, I often think of the word composer, like a composer of music who's going to write or make music. I often think of just that base word compose, where we put the pieces together. And that's exactly what we're going to do here, just with functions. So, if we look at function composition and we just talk a little bit generically about f of x, which equals x squared, and g of x equals x plus 1, I might want to write a rule that applies g of x and then applies f of x. And you guys have actually already been doing this. We just haven't given it the fancy name function composition. But as you've been evaluating functions, you have been plugging one into the other. Let's introduce some notation here as well, though. If I were to write a rule that applied g of x and then applied f of x, this is what our notation would look like. We would have f of g of x. That little open circle there, it's like a little tiny O that we put between the two functions. So again, that's just notation. But it also can be written as this, and this is actually the way that I prefer, using all parentheses. And again, it still said f of g of x. And order does matter, which rule we apply first. So it's always important that when we look at the notation to work from the inside out. So I could do this in the other direction too. I could write a rule that applies f of x first and then applies g of x. So notation here would look like g of f of x, or again, the notation that I actually prefer is this, g of f of x. So again, we would apply that rule of f of x first and then g of x. So notation-wise, we're working from the inside out. Okay. Now again, we're just kind of talking generically here, but I want to give you some actual examples of this. So this time we're going to look at the function f of x equals 2x minus 5, and g of x equals x squared minus 3x plus 8. Okay. And it says to determine the following compositions and fully simplify each answer. So the first one that we're going to look at is f of g of 7. Okay. Now keep in mind, if you feel better about it, this is the same as writing f of g of 7. You're welcome to write it either way for my purposes, but you should also be able to recognize either of those notations and know what it is asking you to do. Now, in this case where we have f of g of 7, because we're working from the inside out, that very first thing we have to do is we have to figure out what g of 7 is. So if we want to figure out what g of 7 is, we are going to plug 7 into g of x. So everywhere we see that x, we are putting a 7. So we are looking for g of 7, which is going to equal 7 squared minus 3 times 7 plus 8. Now, notice that as I do this, and this should be true for any time you evaluate a function or plug in, you always want to make sure that you put parentheses around what it is you're plugging in. So I'm putting parentheses around that 7 as I plug it in. Now, keep in mind, order of operations, I have to do 7 squared first. Then I'm going to have minus 3 times 7, which is 21, and then plus 8. So as I do this, I'm going to have 49 minus 21 plus 8, and now I can add these left to right, and I'm going to get 36. Now it is that 36 that I have to plug into f, my outside function. So now I'm looking for f of 36. So it's almost like there's 2 problems built into one here. So f of 36, everywhere I see an x now, I am plugging in 36 into f. So I'm going to have 2 times 36. Again, I'm using those parentheses around 36 because that's what I'm plugging in. Minus 5. So this is going to give me a 72 minus 5, which is 67. So that 67 that we get out at the very end is our answer to the final problem. So f of g of 7 is equal to 67. All right, sticking with the same functions, but this time we want to find g of f of 7. So this is where I can really emphasize to you that the order is important. Notice this time that the inside tells me to do f of 7 first and then plug that result into g. So if you prefer, we can also rewrite this. Okay. So I'm plugging 7 into my function of f first, and then that result will go into g. All right, so over in f, everywhere I see x, I am plugging in a 7. So f of 7 equals 2 times 7 minus 5. That gives me 14 minus 5, which is 9. Now that 9 is what I need to plug into g of x. So everywhere I see an x in g, I am plugging in the number 9. Again, I'm using those parentheses as I plug in. Order of operations here tells me I've got to do 9 squared, which is 81, minus 3 times 9, so minus 27, plus 8, and that gives me 62. So 62 is our final answer here. G of f of 7 equals 62. All right, still sticking with the same f of x and g of x, but this time they're asking me for f of negative 2. Now, notice that in this case, they don't ask me anything about g of x. I am using just the function f of x. So, starting from the inside, I'm going to plug negative 2 into f of x. And then that result, I'm going to plug into f of x again. So, starting with that negative 2, I am plugging in negative 2 everywhere I see an x in f of x. Excuse me. So I have f of negative 2 equals 2 times negative 2 minus 5. So we're looking at negative 4 minus 5, which would be negative 9. Now, notice this time my outside function is still f of x. So I'm actually going to take that negative 9 and plug it back into f of x now. So keep in mind, this problem asks me nothing about g of x. So now I'm looking at f of negative 9, which is going to be 2 times negative 9 minus 5. So we're looking at negative 18 minus 5, which is negative 23. So our final answer here, f of negative 2 equals negative 23. All right, this one is keeping things a little bit more generic and asked me to determine the composition of f of g of x. So notice that in this next example, this is just x. It's not a number, okay? So I am going to keep g of x just like it is, and I am taking this entire g of x, and I am plugging it in to f of x. So everywhere I see an x, I am plugging in the entire quantity x squared minus 3x plus 8. Okay, so again, I like to always show you both notations here. So we're looking for f of g of x, okay? And that means that I'm taking g of x and I am plugging that entire quantity x squared minus 3x plus 8 into my f of x function. So I am going to have f of g of x equals 2 times x squared minus 3x plus 8. And again, this is where those parentheses really become important. I've got to plug in that entire quantity. And then minus 5. So at this point now, we just need to simplify this algebraically. So I'm going to distribute my 2. And we're going to get 2x squared minus 6x plus 16. And then my minus 5 is just coming along for the free ride. And now the last thing that can be simplified here is that 16 minus 5. So we'll combine those like terms to get 2x squared minus 6x plus 11. And that right there is actually my final answer. Notice that I'm not getting a single number out this time. We're keeping things in terms of x, so you should expect that final answer to also be an expression in terms of x. All right, in the next example, very similar, but we're switching the order. So this time, we are looking for hold that thought. I think I've got the same slide in there twice. I do. So we are now looking at g of f of x. Okay. Now, when we look at g of f of x, my inside function is f of x now. So I am taking f of x and I am plugging it into my g of x. So everywhere I see that x, I am plugging in that 2x minus 5. So g of f of x is going to equal, in parentheses, that quantity 2x minus 5, and I'm going to square it, minus 3, and again, in parentheses, that quantity 2x minus 5, and then I have my plus 8. So order is super important, and using those parentheses is also really important. Now, here's the deal on this one. We got to have a little side conversation. When you look at the quantity 2x minus 5 and you're squaring it, this really means 2x minus 5 times 2x minus 5. So this is actually going to have to be FOILed out. When I FOIL this out, my first is going to give me 4x squared. My outer is going to give me a minus 10x. My inner is going to give me a minus 10x. And my last is going to give me a positive 25. When we combine that outer and inner term, we get 4x squared minus 20x plus 25. So it's super important to realize that when you're squaring that binomial, you're actually multiplying it by itself. We've got to FOIL it out. Now, over here in the middle term, we are going to simply distribute, and then that plus 8's coming along for the ride. So we have at this point 4x squared minus 20x plus 25 minus 6x plus 15 plus 8. All right, we've got some like terms we can combine at this point. We can combine the minus 20x and the minus 6x to give me a minus 26x. And we also could combine the 25, the 15, and the 8 to give me a positive 48. So we are going to end up with 4x squared minus 26x plus 48. Boom. That is our final answer there. Now, all the examples we just looked at were algebraic, but we can also do this from a graphing standpoint as well. So you're actually going to see an example like this in your homework. This is actually where I got it from. So they give us a graph of f of x. They give us a graph of g of x. It's important that we take note that the left one's f of x, the right one's g of x, as we go through these examples, because the order is going to be important in which we look at them. So if we go down and we look at the first example, f of g of -5, I get to work from the inside out. So very first thing I'm looking for is g of -5. So I'm going over to my g of x graph, and I'm going to go to the x value of -5, and I'm going to follow that up to my graph and over into my y-axis to find out that g of -5 is equal to 4. And now it's that 4 that I have to plug into f of x. So now I'm looking for f of 4. So now I've got to go over to my f of x graph and look at an x value of 4, follow it down to my graph, and I see that it has a corresponding y value of -5. So that means that f of g of -5 is equal to -5. Purely coincidental there that the -5 that we started with also was the answer. All right, next one up, let's look at g of f of 0. So this time we are starting with f of 0. So we've got to make sure that we're looking at the f of x graph. I am going to go to an x value of 0, follow it up to my graph, and I'm actually already on the y-axis, so f of 0 is going to equal 3. Now my outside function is g, so I'm going to go over to the g of x graph, look for an x value of 3, follow it down to my graph, and I find out that it has a corresponding y value of -4. So g of 3 gave me an output of -4. So that means that g of f of 0 is equal to -4. All right, now similar to the examples we looked at algebraically, these last two, when we check them out, only refer to one function. So f of -2, we are only going to look at that f of x graph. We can temporarily ignore that g of x. All right, so first thing I'm looking for is f of -2. So I'm going to go to my f of x graph and find the x value of -2, follow it down to my graph, and I find out that it has a corresponding y value of -4. So f of -2 equals -4. Now I need to take that -4 and I'm going to plug it into f of x. So I'll do this one in a different color. Let's do this one in red. Now I'm going to go to an x value of -4, still on my f of x graph, follow it up, and I find out that it has a corresponding y value of 4. So f of -2 equals +4. All right, last one here. This one is referring to g of x. It is g of -3. So we are going to start with g of -3. So on my g of x graph, I'm temporarily ignoring my f of x altogether. I'm going to go to an x value of -3, follow it up to my graph, and it has a corresponding y value of 2. Now it's that 2 that I've got to plug back into g of x. So I'm still looking at that same graph, but I'm going to go to an x value of 2, follow it down to the graph, and I find out that it has a corresponding y value of -3. So g of 2 gave me -3. So g of -3 is going to equal -3. Again, pure coincidence on this one that the original input value also happened to be the output value. All right, now, function composition leads us into what's called the difference quotient. The difference quotient will become important in pre-calculus and super important when you get to calculus or business calculus. The difference quotient is this right here. It's the composition of f of x plus h minus f of x all over the quantity h. And in general, that's what's referred to as the difference quotient. Again, it will have more meaning to us later in future math courses, but it's important to introduce it now because it is really just composition of functions. Now, when we look at f of x plus h minus f of x all over h, this problem does a nice job of breaking it down for us in that the very first thing we actually have to do is find f of x plus h. So,